You look at the figure here. It shows us the reaction, the low energy reactants. Somehow have to get a higher energy state as the curve goes up. The energy has to be put into the system. How do I know? Low energy state reactants, delta G is greater than 0. So that energy has to come from somewhere. Now, I told you before, previous lecture in this chapter that some of that energy is going to come from heat, 37 degrees Celsius, 98.6 degrees Fahrenheit. But that's not going to be enough. And for you to accumulate enough energy to get that to happen, millions upon millions of times for every cell, for every minute, that's just not going to work. So we're going to take, our cells have evolved to take the energy from another molecule. A molecule that's in the cell, that a good portion of your metabolism is for making of said molecule. Energy is going to be added in. Where does it come from? Usually comes from ATP, adenosine triphosphate. Okay, you look at it. Now, keep in mind, we biologists, instead of going through and putting all the carbons in, boom, 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 we draw the geometric shapes you see above my head. Every time two lines come together to form a vertex, if there's not an N there or an O, just assume it's a carbon. So you have these carbon chains forming rings. Well, if you look at to the above my head here to the far right, what you see is 3 rings joined together. 2 of the rings have lots of ends. One of the rings, 5-sided, 5-sided carbon ring. Sugar. Sugar we know as ribose. The 2 rings with lots of ends, well, those are nitrogenous bases. What you literally have there is adenosine. The nuclear version of the nucleotide, adenosine. Just think about it. 3 parts of a nucleotide. The sugar, the nitrogenous rings, the phosphate. 1, 2, 3. Right there they are. But there's something extra. What's the extra, you say? Well, it's right here. Those 2 phosphates. This bond right here, putting phosphate to phosphate, took a bit of energy because phosphates don't want to play well together. This bond, putting that 3rd phosphate on there, that took a lot of energy. We go and we start breaking those bonds, pulling off a phosphate, we get some of that energy back. So, ATP plus water, that's a hydrolysis reaction. Remember, add water to break the bonds. You end up with a diphosphate. A triphosphate becomes a diphosphate, 2. A free phosphate, and then a bunch of free energy. That free energy is what's going to accumulate there and is what's going to drive reactions. How much energy? Well, you look right there. Delta G of negative 7.3 kilocalories per mole. Now, relatively speaking, is that a lot? Yeah. There's very few in biology delta G's are going to reach that low. Remember, anything below 0, reactions are going to occur spontaneously. So you start adding in ATP, you're going to drive reactions. That free energy, it's mentioned way up there, a diphosphate plus phosphate, inorganic phosphate and free energy. Some of that's going to go into the reactant. Boom. Some of it's going to be lost. 37 degrees Celsius, 98.6 degrees Fahrenheit. So when you look at this pump, this active pump from the last chapter, the sodium-potassium pump, you notice there at the bottom, ATP gets turned into A diphosphate. That third phosphate's pulled off. The energy from that third phosphate being pulled off is going to be transferred to the pump. Pump is going to take what few sodiums are inside, pump them out. Going to take what few potassium are outside, pump them in. That's how the energy, that's where the energy to do this work comes from.